Okay, this is 2212 Lab 3 with Ian. The purpose of this lab was to analyze circuit behavior across series, parallel, and RC circuits in order to predict the behavior of current carrying, resisting, and capacitating elements. So the fundamental principles we used in this lab were the node rule, which says that current into the node of some circuit has to equal the current out of a node. Loop rule, which kind of goes with node rule, that the sum of all the electrical potential differences in a circuit is zero due to energy conservation. And Ohm's law, which just tells us that voltage equals the current times the resistance of a circuit element. Here's our circuit. Yep. Okay, so for our results, first when we wanted to measure the current and the voltages in this series, we found that they were 17.7 milliamps at the 47 ohm resistor, or at the 100 ohm resistor, and 17.9 milliamps at the 47 ohm resistor. We reverse the connections, and all reversing connections does is, get a negative sign on puts a negative sign in front of the amperage you got with the first direction. And they should, they're close. The differences are due to, errors in the ammeters. They're almost the same thing. We took a voltage measurement at the 100 ohm resistor. We got 2.7 volts. Or that was just for the circuit as a whole. We got 2.7 volts, and the current for the circuit as a whole was 2.6 milliamps. So the electrical potential difference across different series elements. Here we have the battery. The potential difference between the two sides of the battery is 2.6 volts. The 100 ohm resistor was negative 1.7 volts. The 47 ohm resistor was negative 0.7 volts. And the current for the whole circuit was negative 17.7 milliamps. So I have no idea what that thing back there was. The sum of all potential differences, when we measure it, 2.6 minus negative 0.8 plus negative 1.7, 0.1. Theoretically, it would be 0 volts because there would be no difference. There should be no potential difference across the circuit when we sum all these elements together. However, there are going to be slight errors in our ammeter readings, and slight losses due to things like wires, which is why we have 0.1 volts left over. We made it a parallel circuit. The measured voltage was 1.7 volts, and we had 3 measured amperages, as you can see there. And then we calculated the resistances of the different circuit elements. To do this, we said that V equals IR. If we arrange that, V over I equals R, and we have the voltage. We have the voltages here, and we have the circuits here. So when we did that math, we got that the 47 ohm resistor was actually 44.629 ohms. The 100 ohm resistor was 96.045 ohms. And the wires, I say the wires were 5.65 ohms. Truth be told, some combination of the wires, the internal resistance of the wires, because they do have some, and the internal resistance of the ammeters, because again, they're wires, they do have some, sums to 5.65 ohms. We didn't take any measurements of the wires, the ammeters, so we really have no way of telling. But I assigned them to the wires, but really it's a split between the last two of those. And then we made our RC circuit, where we charge a capacitor and use that to light a light bulb. So we measured the charging duration to be 24 seconds and the discharging duration to be 57 seconds. The real problem with that was we have no idea. We really had no equipment to measure the luminosity of it, so we were just eyeballing it. So those numbers are fairly inaccurate, and we don't have a plot, because we didn't do it online. We don't have a plot of luminosity versus time, which complicated it a little bit. We can't really give you a graph of it. So that's an unfortunate little thing there. If we'd used a 20 ohm bulb instead of the 10 ohm bulb we used, it would have glowed brighter, but it would have died out quicker. And you can see, you can just base that on the equation presented right there. It's a pretty simple relationship. Potential errors, human errors, RC measurements were just eyeballed, as we mentioned, and then the ammeters and the voltmeters were acting odd the whole lab, so those are probably a little bit inaccurate. What if we charged the capacitor with no resistor? In theory, it would take 0 time because R would be equal to 0 in this equation. In reality, the battery has some internal resistance and the wires have some internal resistance. So T is not going to equal 0, but it's going to be close. And yeah, that's my lab. Thank you.